Begin the next talk by Schneider of Marseille in France. The title of his talk is Lagrangian acceleration in confined two-dimensional turbulent flow.
PK, thank you very much. First, I would like to thank the organizers for the invitation and the possibility to present some recent work. So we are back to particles, to Lagrangian acceleration. You will see some PDFs. But now we are in the flat world. So back to 2 dimensions. And we are interested in confined domains. So we have some boundary conditions. And we focus, as I already said, on 2 dimensions. My co-authors are Benjamin Kadosh, he's here, just over there, PhD student in Marseille. And just to mention, he's also presenting a poster and using, of course, wavelets for coherent vortex extraction for 3-dimensional flows. Wouter Bos, former postdoc in Marseille, now working for CNRS in Dijon. And Marie Fage, she's also here from Paris. So let's start with a quick outline, motivation, very fast. Then a few words about complex geometries and volume penalization, because what we are doing, we're using a classical Fourier technique, a DNS technique, to take into account no-slip boundary conditions. So we have a classical Fourier pseudo-spectral code, and we add 1 term to get no-slip boundary conditions. Briefly about the discretization of these penalized Navier-Stokes equations, some physical quantities we need later on, and which are slightly different when we have bounded domains. And then the main parts are the Eulerian statistics and the Lagrangian statistics of particles. So let's start with the motivation. So 2-dimensional turbulence, of course, it's not completely real-world turbulence, but there's some interest, especially in oceanography, for the vortex formation in coastal currents. There are also experiments which are quasi-2D, more or less, let's say, in the group of Harry Sweeney for rotating tanks. And what can be seen in most of these experiments or in real-world flows, we have the formation of coherent vortices which are moving around. Concerning numerical simulations of 2-dimensional turbulence in bounded domains, there are, to my knowledge, very few numerical simulations. In the group of David Montgomery, they did some applications of a spectral method using complicated Bessel functions for circular domains. Of course, these simulations were limited due to the numerical complexity, to low Reynolds numbers, and also in the group of Hermann Clarks in Eindhoven, they did recently numerical simulations using Fourier-Chebyshev discretizations. And the aim of the present talk is to study now the influence of these no-slip boundary conditions on the flow dynamics, and in particular on the Eulerian and Lagrangian statistics. So, complex geometries. A sketch for that, we know for simple geometries, especially for Cartesian geometry, we have very efficient solvers for Navier-Stokes available, especially for our periodic square or periodic box. We can do everything, even to very high resolution, and we are dreaming of very, very high resolution now. But if we have complex geometries or boundary conditions, then the problem is we need special numerical methods. And that is well known for a certain time now. Peskin, a medical doctor at Coron, he had the idea how to compute the flow in a beating heart. So he developed a method called surface penalization, which allows to take into account moving geometries. And the idea of all this method, and later on volume penalization by the Bordeaux group, so they also do nice mathematics, Caltagirone, not only good wine, and Glowinski using a mathematical embedding method with Lagrangian multipliers. They had the idea, let's take our complex geometry, put it into a square box, and let's apply our simple, our available solvers to this very simple domain, and then we enforce the boundary conditions by a penalty term. What we are taking here in the following is the volume penalization, and the idea from physical point of view is quite simple. We say we have different porosities here and here. So inside we have the fluid region, and outside we want to model our solid region. So how to model this solid region? The idea is when the porosity is tending to 0, our fluid becomes a solid. So we solve our fluid equations in the whole domain, and we just modify the porosity. And in terms of mathematics, so we have our Navier-Stokes equation, incompressible Navier-Stokes equation. We add one term with a characteristic function, with a mask function chi here, which is 1 inside our solid region and 0 in the fluid region. What does this mean? This means in the fluid region we have our normal Navier-Stokes equation. But in the solid region we have an additional term with a parameter 1 over eta, which corresponds to the permeability of our solid. So that's a small parameter, of course. And we modify our equations, and it has been shown in a paper by Angot, Bruno, Fabry, again the Bordeaux connection in numerische Mathematik, that this equation here, the penalized equation, tends towards the Navier-Stokes equation with no-slip boundary conditions. So we can recover no-slip boundary conditions in the limit when eta is very small. In the current context, we are dealing with 2D. So we take the curl of this equation, we get our vorticity transport equation, and here we get the curl of this penalization term, which has to be discretized in a suitable way. Just a few words now about the discretization of the penalized equations, nothing special. So we have our bigger domain, our square domain. We are interested in a circular domain, so we will embed our circular domain into the larger square domain. And we have this equation. We have to choose in a suitable way our penalization parameter. Here we did several numerical tests and validation of the code too. So we apply a classical pseudo-spectral method, developing vorticity into Fourier modes, de-LEIs, some adaptive time stepping. And if you're interested, you can find some validation in this Computers and Fluids paper, where we have some numerical tests for that. Now let's define some physical quantities we need later on. So circulation of the flow, energy as usual, entropy also, L2 norm of vorticity, and the palinstrophy, the L2 norm of the gradients, or the squared L2 norm with a factor of 1/2. And now let's look at the energy and entropy dissipation. For periodic domains, we know that for the energy dissipation we have the energy dissipation, which is equal to minus twice viscosity times entropy, which also holds for no slip boundary conditions in bounded domains, because velocity is vanishing at the boundary. Now let's look at entropy dissipation. For entropy dissipation, we know entropy dissipation is equal to minus 2 times viscosity times palinstropy in periodic domains, but in no slip domains we have an additional term due to the boundary conditions. This term doesn't vanish. So we have to compute the surface integral of the vorticity and the vorticity gradients perpendicular to the wall. And also from a mathematical point of view, a nice question could be what happens with this term when viscosity is tending to 0, because maybe the gradients will increase. So that's a question I think which is not yet completely known. Angular momentum is also of some interest if we have bounded domains, which is normally defined as a vector product of the radius from the center and the velocity, but it can be shown when the stream function vanishes at the boundary. It can be directly computed from the stream function, and recently this got some interest concerning spin up of hydrodynamic turbulence in 2D, the work of Hermann Clerks. So now let's come to the simulation and the Eulerian statistics. So this is our big domain here. This black region corresponds to our solid region, and inside we have our fluid region. Resolution is given here, the Reynolds number based on the integral scale, and on the energy is about 50,000 at the beginning. And let's do some simulations starting with random initial conditions. Vorticity is shown. We are on the south hemisphere because the red vortices are turning clockwise. So we are more in Australia, not here. And what we can see at the beginning, we see the formation of coherent vortices, the typical behavior of two-dimensional isotopic turbulence in the center of the domain. You see co-rotating vortices are merging, and counter-rotating vortices are traveling as a dipole. Another feature, what we can see is what happens at the boundary here. We can see thin layers of vorticity at the boundary which destabilize, which roll up into coherent vortices, and we can see that these coherent vortices are then ejected into the bulk flow, and this is a kind of a forcing mechanism, as we will see later on. So we have the generation of vorticity and vorticity gradients at the boundary. Just to show the stiffness from numerical point of view, a cut here, the given time instant of vorticity, and the two velocity components. Velocity, again, is quite smooth, but for vorticity, we can observe, especially near the boundary, we have a very spiky behavior, and well, it's quite intermittent, the vorticity itself, as we will see later on. For the stream function, why do I show that? Just to see, well, we have vortices in the bulk flow, but also the stream function illustrates that we have vortices near the boundary. Now let's look at integral quantities like energy, entropy, and palindrophy plotted over time. For energy, we can see, as usual in two-dimensional turbulence, we have only very slow decay of energy over time in terms of eddy turnover times here. For entropy, we see again some decay at the beginning. We see even a self-similar decay, which is much slower than for isotopic turbulence, where we have typically a slope between -1 and -2, depending on the simulation. So we have a slower decay here. And what is different to isotopic turbulence is the fact that we have a non-monotonous behavior. That means we have some oscillations here. Sometimes entropy is generated, and that is due to the forcing. And that can be seen directly if we look at the palindrophy. Again, we have some decay here, and then we see a strong generation of vorticity gradients over time due to the boundary conditions. If you plot the same quantities in log-lin representation, you can see for a certain amount of time we have an almost steady behavior of our flow, but of course for longer time we see a decay of the flow.
Is that a plane average?
That's, yeah, it's just an integral over the circle, yes. Well, then mean square wave number, also it's non-monotonous in the for the decay behavior, which is different to periodic domains. And now to come back to the point of entropy production at the boundary, we can plot the different terms for the dissipation of entropy. So entropy dissipation, this curve here. And the entropy production, what is interesting, okay, let's say at the beginning it's decaying, but later on we have entropy production, which almost has the same values as the dissipation itself in the periodic domain. That means that the sum of the two terms is very small, which implies that the entropy dissipation for this time period is almost vanishing, which shows that we have a quasi-steady behavior for several hundred eddy turnover times. Concerning the L-infinity norm, also min max of vorticity, we see again this non-monotonous behavior. And just a quick remark about angular momentum. I don't want to go too much into detail. We see no spin up here. It's oscillating around 0. This confirms the conjecture of David Montgomery that in axisymmetric geometries we don't have a spin up. And what Hermann Clark showed for square containers, they found a strong spin up, which becomes even stronger if we go to higher Reynolds number in a recent paper in PhysRev-E. And in MHD, just to make some publicity, we did some recent work for MHD flow in bounded containers with boundary conditions using a very similar technique, and we found spin up in square containers, which means that our MHD flow starts to rotate in one preferred direction. Concerning Eulerian statistics, let's look at the PDF. We saw a lot of PDFs today. So some more PDFs of vorticity first. So the initial condition is Gaussian. The pressure also initial condition is Gaussian. And then when time goes on, we see an intermittent behavior. We see heavy tails in the vorticity distribution, which corresponds to the coherent vortices. And that's nicely illustrated if you look at the pressure PDF, where we have a skewed behavior and exponential tails for negative pressure values. which are directly a signature of our coherent vortices. So let's do some half-time conclusions. Before going to the Lagrangian part, we performed DNS in the circular geometry using a classical numerical method, but using an original technique to take into account no-slip boundary conditions. This technique is also working for moving obstacles, and right now we are computing, for example, flapping wings, some insect flights, using this kind of techniques, again with the pseudospectral method. We've seen for turbulence that the no-slip boundaries play a crucial role for the decay, because we see some forcing due to the boundary. At early times, of course, we have the self-organization of the flow, similar to flows in the isotopic case, but at later times, we see that the coherent vortices at the boundary compensate the entropy dissipation, and the flow decay rate is drastically reduced later on. That can be shown in the time evolution of entropy and palinstrophy, where we don't see a monotonous decay. And for the pressure PDF, we saw it's skewed, and we have exponential shape, which confirms the existence of coherent vortices. For the second part now, what we did, that's essentially Benjamin's work. He put now Lagrangian tracers into the flow, and we performed Lagrangian statistics to look at the classical question of Lagrangian acceleration. We studied a little bit the literature also, and to the best of our knowledge, we were really surprised that for two-dimensional turbulence, we didn't see Lagrangian acceleration. There's one paper now which just appeared in Physica D by the group of Friedrich from Münster in the special issue of the Oswa conference, but apparently there are no publications on Lagrangian acceleration in 2D. And for bounded domains, we didn't see them neither. So we put some particles, about 1,000, into the flow. Our flow is decaying, so we have to apply a technique to get stationary statistics. And here we're using the technique by pK to divide our Lagrangian quantities by the standard deviation at each time instant to get stationary statistics. And now again, what we did, we put our particles in the vorticity field. The particles are in pink, what you can see here, a little bit difficult to see. And we computed the trajectory of the particles, and we are comparing two different geometries. Our periodic geometry and our circular geometry. And for the circular geometry, we are especially interested what happens at the boundary. So inside the flow, it's very similar to isotopic turbulence, but near the boundary, we see a completely different behavior. So this particle is now approaching the boundary. Here we have our no-slip boundary conditions. So velocity will be very small, and we have to wait for some time that our particle will advance in time. So this will take some time, but we still follow this particle, because then something will happen. What will happen? We have our boundary layer here, and the boundary layer will destabilize. It will roll up. You see the acceleration which is coming. We see the formation of a vortex here, which is traveling into the bulk flow, and here we had a very strong acceleration of the particle. That can be summarized. It's blinking. If we plot now different typical particles, for example, we have chosen 3 particles here, one with a weak acceleration, intermediate and strong acceleration. And what you can see on this graph is the trajectory of the part of one particle colored with the modulus of its Lagrangian acceleration, but normalized with the maximum of the modulus of acceleration. So strong acceleration is red, and weak acceleration is blue. So what you can see here, we don't have strong values for the first particle. It's traveling inside, and we have some acceleration all the time. If we look at the particle we just saw before, inside the flow again we have very weak values. It's moving slowly, but then when the boundary layer detaches, we get one very strong acceleration, what you can see here and then our particle travels again inside the flow. And another example here again, for this particle near the boundary we have some extreme acceleration. Now we have to quantify this statistically. First we looked at Lagrangian PDFs of Lagrangian velocity and compared periodic with circular geometry as expected. So for velocity it's not very interesting, we get a Gaussian behavior. For periodic as predicted, and for the circular geometry the only slight difference is near zero we can see that we have no slip boundary conditions. We have a small peak here which is coming from our boundary conditions, nothing else, but it's still very much Gaussian. Next point is, let's take the increments. On the left side the periodic geometry, on the right side our circular geometry with no slip boundary conditions. So what can we see? For a large increment size we get our velocity, nice Gaussian distribution on the left and on the right. The PDFs have been normalized by the variance in the usual way. What we can see if we decrease the size of our increment, of course we get the acceleration finally. We see that the tails are becoming heavier and heavier, what we saw in the talks this morning. But now the major difference between the periodic and the circular geometry is that the acceleration is completely different, at least for the tails. So you can see we get very heavy tails which are probably due to the no-slip boundary conditions. So now we can quantify the difference by plotting the flatness of the increments as a function of the increment size. If the increment size is large, we get the value around 3, which correspond to Gaussian values. And then, when the increment size is decreasing, well, we get closer and closer to the acceleration for our increments, and we can see that the flatness for the periodic case increases. And the difference is, for the no-slip case, the flatness is increasing much more, and we get very high flatness values, which are due to the boundary. Now let's superimpose both acceleration PDFs, the periodic one and the circular one, and we can see near the center. So for weak acceleration values, we get very similar behaviors, but for extreme values of acceleration, we see our heavy tails, which are present in the circular geometry. And we can even see some algebraic behavior when we plot it in log-log with a slope -4. And the next question is now, can we quantify the influence of the boundary? And to quantify the influence of the boundary, what can we do? We can study our statistics using some conditioning. That means we just study our particle statistics inside a circle, and then we change the size of our circle to see what is the influence of the boundary. And that's exactly what we did. So here we have a virtual circle, and we can do the statistics just inside this circle. And then we subsequently increase the size of our circle to see how the statistics are changing. We did that. We plotted the conditional flatness of the Lagrangian acceleration as a function of this radius of our virtual circle. And we see in the center of the domain, well, the flatness is not very large. But then suddenly something happens. Flatness is increasing, and it's going up to the value 30 if we take the whole domain. That means that in the center of our domain, the boundary doesn't play a significant role, but there's a huge part of our domain where the Lagrangian acceleration is modified due to the no-slip boundary conditions. And that allows to define or to introduce Lagrangian boundary layer thickness around here, 0.3, which shows that a huge part of the domain is influenced by the no-slip boundary conditions. So the conclusion, second part, is we studied the influence of no-slip boundaries in 2D turbulence on Lagrangian velocity and acceleration. For velocity, we don't see any significant influence, as expected, only a small cusp around 0 due to the no-slip conditions. But for the acceleration, the picture is quite different. We see heavy tails in the Lagrangian acceleration, extreme values, and using conditional statistics, we are able to quantify the thickness of a Lagrangian boundary layer. And that is now a little bit surprising, because finally what we can see that a huge part of our domain is influenced by these no-slip boundary conditions. That is, in our case, it's about 90% of the domain surface which is modified due to the generation of vortices at the boundary. If you're interested, there's a paper where you can find these results for the Lagrangian part. And the question now is future work, what to do next, of course. There are a lot of things to be done. One question is, what is the influence of the Reynolds number on the Lagrangian statistics? Another point is a comparison with Eulerian quantities to compute also Eulerian acceleration and to compare it with Lagrangian acceleration in this bounded domain. And one question is also, and here I think we have to think about that a little bit in more detail. For 3D, of course, we have to do it. That's also one perspective. It's a question of time to do it in 3D with boundary conditions. The question is, if really the walls play such an important role on the Lagrangian statistics, perhaps we have to think about that in more detail, and we have to perform some conditional statistics of our particles, which can be done to see what is the influence of the wall. I think here I will stop to leave some time for questions. Thank you.
You try to compare with the theory of Lebedev and Kurizin on this wall-determined mixing, the theory of...
No, we were not comparing that, no. That's perhaps something we can discuss about that.
Last
Are you confident that you're resolving your boundary layers with the...
Yes, concerning code validation, we did, there's a paper in Journal of Computational Physics where we did dipole ball interaction to study the influence of the penalization parameter. It appeared last year in JCP. So from the code side, we are sure on the safe side. So, resolution is sufficient.
That's one more question. Have you done spectra as well for these
No,
statistics?
That's one point which should be done. But the problem doing Lagrangian spectra is it's very difficult to see some inertial range in the Lagrangian spectra. I think Benjamin, he plotted some spectra, but we were not so happy in this case because, well, the inertial range is too small.
You try also to make some forced simulation.
Yes, these simulations are currently underway. You can discuss that with Benjamin. He's running simulations where we are applying a forcing technique in this cylindrical geometry also. Yes. And it's important, I think, to have also non-decaying flows with boundary conditions.
Actually, I have a question. We go back to your figure 6, I believe.
Yeah. Oops.
Where you are showing the fatness factors of the Lagrangian velocity increments.
Yeah.
Yes, this. So, here the dotted line more or less converge, but the solid line is not.
No.
And you say that it means that the fatness factor of the acceleration is really high.
Yes.
Do you have an explanation why that is so?
About convergence, we computed the flatness of acceleration, and the flatness of acceleration is about 30. What is a little bit surprising is perhaps the shape of this curve. Here, I think your question is why we don't get some kind of saturation.
Well, if you have values of tau small, going smaller, 101, 1001, and so forth.
Okay, here we are on the limit of the numerical resolution because it depends what is the sampling time of our trajectories. So here we have a limitation. I think that has to be checked in future work. We limited ourselves here because after that we are not confident anymore.
Any other question?